welcome back. It seems like maybe this video won't have our strange yellow and white oscillating leggings, so maybe this one will be a little easier to watch, right? Last time, what did we do in that fun video? We looked at a constant coefficient second order homogeneous ODE. So that's where we're going to stay for a little while. We're in section 2.2. Today we're going to add in a little bit of 2.1. We're going to maneuver a variety of different topics in a slightly different order and in much more depth than is in the book. So we're going to stay here for a while. That's why you'll see the due date for section 2.2 to just keep extending until we get through enough that you can actually do all the problems in there. So we're going to give a lot more theory behind why everything works, okay? All right, so what did we do last time? We constants, where the leading constant is not 0, because then it wouldn't be a second order constant coefficient homogeneous ODE, right? And what did we say the idea was? We assume that we have a solution maybe that looks like this based on our knowledge of exponential functions and their derivatives. That took this calculus problem, this differential equation saying, find me all functions out there in the world where the constant a times the second derivative plus the constant b times the first derivative plus the constant c times the function itself is equal to 0 for some specific constants a, b, and c, right? And we took this calculus differential equations problem and turned it into an algebra problem, right? That's why this guy is called the characteristic equation for this differential equation, because it's just a quadratic equation, and we know there are 3 cases to a quadratic equation. In case 2 and case 3, right? You know, yet to come, okay? Yet to come. We haven't talked about the other 2 cases yet. We're still in this case. So where are we? What if the quadratic has distinct, different, real, right? Real numbers, roots. So 2 distinct, it's a quadratic equation, so it has 2 roots. What if they're real and they're different, okay? And we saw then that just determines for us 2 solutions. One would be, we'll call y1 e to the r1x, one of those roots, and y2 would be e to the r2x, one of those roots. We did an example last time. There's another example in your book for specific constants a, b, and c, and specific roots that come out r1 and r2. Okay, so now we have this differential equation. The question was, what are all solutions, right? What are all solutions all functions y that satisfy this ODE, okay, for a specific a, b, and c. And what we've got is 2 solutions. 2 is not bad, right? 2 is good, right? 2 is better than 1, right? Okay, so we've got 2 solutions, and you can double check that they're a solution for a specific problem. If you're doing a specific problem, you get out solutions, and then you can just take derivatives, plug in, and make sure you get what you get, right? If you don't get 0, then you know did your quadratic equation wrong, or you factored wrong, right? Okay, the big question then is what? Okay, what we want to know, so we have 2 solutions, right? But we want all solutions, right? That's what we want. We want all solutions. Last time, we saw that if we know these 2 guys satisfy the equation, then what else did? These 2 specific values of r, what else did? Last time we saw that and I'll give you some terminology again, a linear combination of y1 and y2 A linear combination of y1 and y2. What is a linear combination of y1 and y2? I combine these two things linearly, which means I multiply by a constant and add. So that's a linear combination of y1 and y2. Multiply each one by its own constant and add those two together. That's what a linear combination is. Okay, so last time what did we see? We saw that a linear combination of y1 and y2 also satisfies the ODE. Right? We did that by explicitly putting that in, taking the derivatives, right? Regrouping, right? Using distributive law and what we know we're allowed to do with derivatives, with sum rule, right? Okay, another way to do that super easily, right? So another way to do that is to use operator notation. To write that simply, to write what we did last time simply is to use operator notation. What does that mean? Right, what did we do? We plugged that all into here, right? Into there, and then we distributed everything. So what would operator notation say? Operator notation say, well, okay, well, let's let L of y mean A times y double prime plus B times y prime plus C times y. Okay? So the operator L, or linear operator, talk more about what that means eventually, acting on a function y does what? It creates this combination. The number A times its second derivative plus the number B times its first derivative plus the number C times y. Okay? So last time, we showed, well, I'm going to write it in operator notation this time, that if we take L and we evaluate at C1y1 plus C2y2, right? We put that expression in for y in each spot, right? That what we got was C1 times L of y1 plus C2 times L of y2. You can check that for yourselves, again, just by going through this idea. We did it with one constant and we did it with a sum. So this is doing it now all together at once, right? So you can do that for fun for yourselves, to justify for yourselves that this is a true statement. If you put that guy in, distribute the derivatives and all of that, redistribute. And what do we know, right? Well, y1 was a solution, right? y1 was a solution, and so what is L of y1 equal to? Right. A y1 double prime plus B y1 prime plus C y1. That's L of y1, but it's a solution, and therefore that equals 0. Okay? Because y1 is a solution. Yeah? Plus C2 times L of y2. Well, what is L of y2? Well, L of y2 is A y2 double prime plus B y2 prime plus C y2, right? That's easy enough to, L of y2. You just put a y2 everywhere, it's all y, right? But what is y2? y2 is this guy who we said is a solution of this equation. So what does L of y2 have to equal? 0. Good. Okay, and this guy is because y2 is a solution. You can see why operator notation ends up becoming a lot simpler to utilize. We justified this last time. You should justify by putting in the details. We did it separately, like I said, once by adding and once by multiplying one of them by a constant. See that you can do it if you just dive straight in with this. And so therefore C1 times 0 plus C2 times 0 is just 0. And so L of this expression is 0, and therefore this is also a solution, right? Okay? So also satisfies the ODE is the same as saying that L of C1y1 plus C2y2 is equal to 0. Okay? All right, so now we've got a wider class of solutions, okay? We've got a wider class of solutions, and so now our question becomes, use this maybe. Now our question becomes what? It becomes, okay, does this guy contain all solutions, right? Before we had two, this guy and this guy. We add them together, multiplied by a constant, create a linear combination, and now we have infinitely many solutions. So does this expression of infinitely, why is it infinitely many solutions? Because we have two arbitrary constants, right? That's infinitely, it's a 2 degrees of freedom, infinitely many solutions, right? Okay, 2 degrees of freedom. So now our question becomes, does this expression of infinitely many solutions contain all possible solutions? We call this star, right? That's what we were calling it, 2 star. Right? Is it, can we be assured that as long as we say, so what is another thing, what is another way to say that? If we let y equal that, can we call that the general solution? So is y equal this the general solution of star? Right? Okay? It's the general solution. Why would it be called the general solution? A general solution contains all possible solutions, right? Okay? Other terminology for that. Other terminology for that is the set y1, y2, that set of functions, right, over here, is that a fundamental solution set. Fundamental solution set for the differential equation, okay? It's a fundamental solution set. These are curly braces, right? They don't look so good, right? They're just, there we go, right? It's a set of 2 elements, right? Those 2 solutions, are they a fundamental solution set? What's a fundamental solution set? A solution set where if I create the linear combination, it contains all possible solutions of the differential equation, okay? So that's our big question, all right? So we would like to know the answer to that. We would like to know if I went through this nice, awesome, super simple idea where this differential equation gives me this algebraic quadratic equation, which I can always figure out its roots. Right now we only know what to do in case 1, right? Then are these 2 solutions going to determine all possible solutions? Okay? Are these 2 solutions? We also call that, do these 2 solutions span the solution space? Do they span the solution space? Those are words that will come up a little bit later in the semester. Okay, so what do we do? Well, when we ask questions like that, we usually want some type of theory to be grounded in, right? So let's do that. Okay, so here's a theorem. If y1, which is some function of x, right, and y2, which is some function of x, are any 2 two solutions, any two solutions to our second order constant coefficient ODE, homogeneous ODE. Well, that's good right now, any, because we have two solutions, right? Not quite. You can't just pick any two solutions, not just any two solutions. A linear combination will represent all possible solutions. There's got to be something special about those two solutions and the way they interact. So, what is that special thing? They've got to be linearly independent. Linearly independent. And here, since we're only talking about constant coefficient problems, and we had said with our earlier theorem that we'll have solutions that exist in constant coefficient ODEs for the entire interval for the independent variable. That's awesome. We'll generalize that to non-constant coefficients and see where the trouble comes later. Then, right, so here's the extra condition. Then there exists unique constants C1 and C2, and I'll write it out. Unique constants C1 and C2, so that if I create the linear combination C1y1 plus C2y2, then that will satisfy the initial value problem. What is the initial value problem? Just to make my life, our ODE, right? AY double prime plus BY prime plus CY equals 0, right? Our ODE, right? Plus the initial conditions that Y at some initial value of X is some number, we'll just call it alpha, like before I think we used, and Y prime at X naught is some other number, beta, okay? So there, as long as these two guys are linearly independent, we'll always be able to satisfy the initial value problem, and since we can satisfy any arbitrary initial value problem, then we have the unique solution, and we've got all the possible solutions that we need, okay? So, this magical thing, linear independence, what is it, right? We want to know, did those two solutions that we had, are they linearly independent? Because if they are, we're golden, right? We have now determined all possible solutions. So that's going to take a little while for us to figure out how to even talk about this concept. Okay, so here we go. There's a variety of ways we're going to talk about this concept. For us, right now, we're only talking about two functions that are linearly independent. As we move along, we're going to want to be able to talk about multiple functions being linearly independent. So right now, this is a special case, really, of a much more broad topic, okay? Much more broad topic, just to be clear. So before we define what linear independence is for two functions, a lot of times it's kind of useful to kind of know what it isn't sometimes, right? When you're trying to figure out what something is, it's sometimes really more useful to think about what it isn't first. So let's do that. You guys good? Okay. All right. So here's a definition. Let's first define what it means to be linearly dependent, yeah? Because that would be the opposite of being linearly independent. If you're not linearly independent, you're linearly dependent, yeah? Okay, so we say two functions, y1 and y2, I'll just write of x, or whatever the independent variable has to be, or it is for that problem. So two functions, y1 and y2, are said to be linearly dependent I, so the interval matters, right? Okay, as well. An interval I, if and only if, here's the definition coming, there exists constants C1 and C2, okay? Not both 0, okay? Not both 0, such that what? I look at a linear combination of my two functions, C1y1 plus C2y2, and I set it equal to 0 for all x, whatever your dependent variable is, in the interval, right? So what does it mean to be linearly dependent? If I can satisfy this equation, linearly dependent, y1 and y2 are linearly dependent if we can satisfy this equation without requiring both C1 and C2 to be 0. Now, obviously, if C1 and C2 are both 0, this equation holds, right? 0 times y1 plus 0 times y2 is 0. But that's not the idea here, is can you satisfy this equation with two constants not both 0? Linear combination set equal to 0 for all x in the interval. Are there constants that are not both 0 that will do that? If so, the two functions are linearly dependent, which is not what we want for generating our fundamental solutions that a fundamental solution set that gives us the general solution to an ODE, right? Okay? All right, so let's look at another way to phrase this, okay? There are many ways to state what the definition might be, whether we're talking about two functions or multiple functions, but for right now we're talking about two functions, because that's all we're gonna get our feet wet with two functions, okay? So let's think about that. What does that mean? Well, if we can satisfy this equation with our constant not both 0, so for example, if C1 is not 0, right? If C1 is not 0, then I can solve this equation, right? For which variable? For which function? Well, if C1 isn't 0, that means I can divide by it, right? Okay? And so I could say, if C1 isn't 0, then what happens with this equation? I would get C1y1 is minus C2y2, right? Yeah, bringing that guy across and then divide by C1. And so I've got that. And it's critical that C1 isn't 0 because I'm dividing by C1, right? And what if we were in the other case where C2 wasn't 0? Well, then I could say C2y2 is minus C1y1, right? And then I could divide by C2 and solve for y2 in terms of y1, right? Either way, whichever way it is, what I basically have is one function is a constant multiple of the other function. One function is a constant multiple of the other function. So linear dependence is a lot simpler with just two functions, right? So we can also say y1 and y2 are really y1 and y2 are just two functions. Let's just say that. So two functions are linearly dependent, LD, right? Linearly dependent if one is a constant multiple of the other. Okay? It simplifies for two functions, all right? That's what this is saying. So let's look at an example, right? Of the other what? On all of I, right? Right? On the entire interval, not just that one value, okay? All right. So hopefully you see why that guy and that guy are equivalent. Let's look at an example. Okay, y1 of x, let that be x to the 6th, okay? And y2 of x is 3 times e to the 6th natural log of x. Okay? Question. Are y1 and y2 linearly dependent? Now, I'm talking about linear dependence, right? We have it. That's what our eventual goal is to talk about linear independence, right? So what is this the same as, right? Also known as, right? Just two functions is one of y1 or y2 a multiple of the other. A what type of multiple? Matters. Constant multiple, yeah, right? Constant multiple. How's the other? Okay, what do you think? One of those functions a constant multiple of the other. What do you think? Yes? No? Be a little careful there. Let's see. At first sight, they don't seem like it, right? At first sight, you're like, no, they are not constant multiples of each other. Right? Here's a constant, right? Times some function that's not that function, so, you know, no. Oh, but wait. From your excellent work in section 1.4, as soon as we saw this, we were like, hey, wait a minute, I know what's going on here, right? What can I do with this 6 right here? Very nice. Natural log properties, I can move it up there, right? So this function is the same as 3 times e to the natural log of x to the 6th, right? I cannot use the fact that e and ln undo each other until I get that 6 out of there. And the way to get it out of there is with natural log algebra, right? And now, that function is the same as this function. But what is e to the natural log of x to the 6th? Yeah, right, there we are. It's 3. So I've got my 3 here. That the e to the natural log of thing is thing. So what is y2? And y2 is 3x to the 6th. Okay. Is one of y1 or y2 a constant multiple of the other? Well, yes, indeed. Right? y2, which is 3x to the 6th, is 3 times y1, right? And therefore, y2 is a constant multiple of y1. And so, are y1 and y2 linearly dependent? Yes, because they are constant multiples of each other. So those two functions are not linearly independent functions, and so they could not be a fundamental solution set for a differential equation, right? Okay, all right. So this constant multiple is true on all of the real numbers, right? So this is true on minus infinity to infinity, right? Okay, so these guys are linearly dependent on minus infinity to infinity, okay? Yeah? Okay. Nice. Okay, before we, that's the simple way to think about it, constant multiple. But it's worth looking at how it relates to this, with this equation, just because, remember, we're gonna wanna do this with more than just two functions. So we're gonna want more insights into what's really going on behind the scenes here too. Okay, so let's look at that another way. Okay, so seen another way. Okay, what do we have? Well, let's write down our linear combination. Right? What is that? C1 x to the 6 plus C2. Let's just use our original guide, right? 3e to the 6 natural log of x, right? That's our linear combination. But what do we know from our work we just did? This guy is just 3x to the 6th, right? Okay? So, our question is, we want to consider setting this, I'm just going to write it as 3c2 because that's the way we would write it, right? We want to set that equal to 0, okay, for all x minus infinity to infinity. We want that to be equal to 0 for all x, right? Notice that's a very different thing, right, than saying, like, whatever we had with a quadratic equation. Like if you have 3r squared plus r, plus 2, whatever, is equal to 0, that's a quadratic equation, and you're looking for two roots r that solve this equation, right? We don't want this to be true for all possible r, okay? We know it's only true for two values of r. Here, we want this equation to be true for all values of x, okay? Well, what would we do? We would factor out an x to the 6th, right? And we have c1 plus 3c2 has to be 0, right? If that's going to be the case. So what do we know? If x is not 0, right, then this term is not 0, and we need this to hold for all values of x, and so therefore, what would that mean? That would mean c1 would have to be minus 3c2, yeah? Okay? So what do we kind of discover here? What is this telling us, right? What is this telling us? We can make this equation hold, in this case, as long as we choose c1 to be equal to negative 3c2. Yeah? What does that mean? That means there are infinitely many pairs of constants, c1 and c2, that solve our linear dependence equation, right? Linear dependence equation, right? This is our linear dependence equation for this particular problem. For example, right, there's infinitely many, right? I could take C2 to be 1, and then what would C1 be? Yeah, negative 3, right? You've got your relationship right there. If C2 is 1, C1 needs to be negative 3, then that equation says 0 equals 0, right? I could take C2 to be negative 5. If I take C2 to be negative 5, what should C1 be? Good, 15. Right? 15x to the 6 plus 3 times negative 5x to the 6 is 0, always, right? For all x, yes? Okay? And there's infinitely many more pairs of constants. As long as they satisfy this relationship, right, we can make this equation 0 for C1 and C2, not both 0, right? Yeah? Okay. So there's infinitely many possible choices, right? All we really needed was one. Okay. So these guys are linearly dependent. That's another nice way to think about it, and that will be useful for us later as well, especially when we generalize to more dimensions. right? This is only two-dimensional. We only have two solutions, yeah? Okay, so now that we've got that idea, lots of different ways to think about the same thing. Let's talk about what it means for two functions to be linearly independent, okay? Linearly independent. So, again, just for two functions, well, it means they're not linearly dependent, right? Okay, so y1 and y2 are linearly independent on an interval I, right? Some set of values for the independent variable, right? If and only if, well, there's a lot of ways we can say not linearly dependent, right? One very simple way to say it is that they are not constant multiples of each other, right? Okay, so if and only if y1 and y2 are not, only if and only if one is not a constant multiple of the other. So it's simpler to say it that way. How about neither is a constant multiple of the other? Right? Okay? That's one way to say it. Let's look at another way to say it as well, right? Again, on all of I, right? Very different than solving for roots, right? Okay? Okay. Or, another way to say it, okay, is that, so I guess we'll just, like, this piece goes along for the ride, and then we're going to give a new if and only if, right? Okay? y1 and y2 are linearly independent on I, if and only if, what? I'm going to say it in words first, because it's kind of a strange equation, okay? So, setting the linear combination, we know what that means now, right? To 0 has only, well, you guys tell me, right? What did we say? If we wanted to not be linearly dependent, then we want to be able to, if linear independence is not linearly dependent, then this equation, right? This is setting the linear combination equal to 0. This equation should only be able to be satisfied if what? You know it, if what is true? Yeah, C1 and C2 are both 0, right? Violate that guy. All right. So if setting the linear combination to 0 has only the solution C1 equals C2 equals 0. How do we say that in math, right? How do we say that in math? We say C1 y1 plus C2 y2 equals 0 implies C1 equals C2 equals 0, right? Okay? On I, right? For X in I. Yeah? Another way to say that, right? This is an implication, right? We could say that with an if-then statement, right? If C1 y1 plus C2 y2 is equal to 0 for all X in I, then C1 equals C2 equals 0, well, it doesn't really kind of work that way, right? So we're trying to say if the only solution of this is that, so if setting that equals 0 implies that, then it's going to be too many thens. So if that equals 0, we'll just maybe say it like this, implies that has to equal 0 is the only solution, then y1 and y2 are linearly independent, Li, right? Linearly independent. Okay, so let's go do some examples of that. the only way to satisfy this equation is by making both constants 0. These concepts are central to so many things. In linear algebra, differential equations, and beyond. Okay. Let's go back to let's see an example. Linear independence. Let's go back to our two solutions from our from our ODE example last time. What was that ODE that we did? Y double prime minus 9y prime equals 0, right? Isn't that it? What's the characteristic equation that comes from this, right? R squared minus 9r equals 0. You should be able to do that, right? Immediately, not have to go through all the work that we did to get that, right? So now what? Factor out an r minus 9, maybe it was a plus, because we had a negative 9, that's what it was. Plus, yeah, there we go. So what does this mean? R is 0, or r is negative 9, right? That gives us a y1, which is e to the 0x, right? So this guy's like our r1, this is our r2. We're in the distinct different roots, right? Distinct real roots. 0 and negative 9 are different numbers, and real numbers, right? But e to the 0 times x is just 1. What is y2? y2 was e to the r2x. So that was a really, really quick rundown of that problem, right? We did that. So here are our two solutions, right? Okay. So, question, are y1 equals 1 and y2 equals e to the negative 9x linearly independent? Where on minus infinity to infinity, right? Why do we want to know the answer to that question? Remember where we started? Where did we start this whole process, right? We want to know the answer to that question because if the answer is yes, then we can say that those two guys are a fundamental solution set to this differential equation, and therefore every solution, the general solution, will just be the linear combination of those guys. That's a big deal, right? Okay. So, are they linearly independent? How do we decide? Okay. A lot of different ways. So let's look at it this way. Okay, so option 1. Is one of them a constant multiple of the other, right? Well, we saw from what we did with our definition of linearly dependent, it doesn't really matter if one is a constant multiple of the other, then the other is the constant multiple of that one too, right? It's just a different constant, right? With our other linearly dependent example, we could have done it differently and said 1/3 y1 is y2, right? So y2 was a constant multiple of 1/3 times y1, or vice versa. That's really what I meant. You know what I mean. Go back and look. So anyway, is e to the negative 9x a constant multiple of 1? Well, no, duh, right? Of course not, right? How would you say that in math, right? E to the negative 9x equal a constant times 1, right? Is that possible? Well, absolutely not, right? Because a constant times 1, this is a constant, and this is a function, right, of x that changes as x changes, because this has to be true for all x in minus infinity, right? Okay, so x changes, and therefore this guy is not constant, and so this is not equal to a constant. So the answer is no. okay? So one is not a constant multiple of the other. Therefore, okay. We could conclude that those two guys are linearly independent. Let's look at it a slightly different way, okay? This way is kind of okay. That's the way your book does it, but it's the quick, fast, easy way to do it, okay? But we're gonna look at it another way just so that we solidify a little more of the way that we're gonna generalize these concepts of linear independence, okay? To more dimensions than just two, okay? So what's another way? Option 2. Okay, option 2. What are we gonna do? We're gonna say, okay, well, for all x in real, okay, let's look at C1 times Y1 plus C2 times Y2 and set that equal to 0, right? That's what this says to do, yeah? Okay? So, what is that? We consider C1 times 1 plus C2 times e to the negative 9x, yeah? And we set that equal to 0, and we ask, does this have solutions other than C1 equals C2 equals 0, right? Okay? Now, it's kind of the same thing as if we brought this across, right? And then would say, oh, nope, that's not equal to a constant, right? Same deal there, okay? So we could do that if we wanted. So if we just write over here, is C1 equals C2 equals 0 the only solution of this equation? Right? We know that solves the equation, but are there other C's hiding out there? So how might you justify that to yourself, right? How might you justify that? Okay, so this has to hold, right, for all x, right? Okay. Since it has to hold for all x real, we could pick some easy x's, right? So let's pick x equals 0. If x is 0, then this equation becomes C1 plus C2, right? E to the 0 is 1. C1 plus C2 is 0, yeah? And let's pick, what's another easy x? Negative 1/9. Why? Just to make my life simpler, right? X is negative 1/9. Let's pick x is negative 1/9. So if x is negative 1/9, then what's the relationship between C1 and C2 have to be? Well, C1 plus C2 times, well, e to the negative 9 times negative 1/9, right? That's just e. Has to be 0, right? Yeah? So this would be the relationship. And we could pick infinitely many more x's, right? And get more relationships. But what we have right now is 2 equations and 2 unknowns, yeah? Okay? So 2 equations, 2 unknowns, we could solve that in a variety of different ways, but since it's just simple 2 equations and 2 unknowns, let's do it the way we might simply think about doing it. Solve this guy for C1, so C1 is negative C2, yeah? And since C1 is negative C2, then let's plug that in here, right? So negative C2 plus C2 times E has to equal 0, right? Okay. Well, what would I do here? Factor, right? I would factor out the C2, and what would I get? Negative 1 plus E has to equal 0, yeah? Right? Right? Where am I going with this? Is negative 1 plus E ever 0? No, right? E is not negative 1, right? E is some number between 2 and 3, yeah? Okay? So this guy is not 0, yeah? So now I have a product of 2 things is 0. That one is never 0, so what has to be true about C2? C2 is 0. And if C2 is 0, then what does this piece mean about C1? So now C1 is negative 0, which is 0. Beautiful, right? So what did we just show? we just showed that the only solution of this equation is C2 and C1 both are 0. And therefore, that's another way to say that our answer here now is yes, right? Is that the only solution? Yes. Therefore, 1 and e to the negative 9x are linearly independent. Are they constant multiples of each other? No. Therefore, 1 and e to the negative 9x are linearly independent, right? Okay? And there's lots of other ways to approach it too, but I think we'll just stop at that for now, or at those two ways, just to end this video at a reasonable time, which we're not doing right now. So, why are we excited about this? Right? Why are we excited about this? So what do we now know? Right? These guys are linearly independent. Yeah? So, what did that buy us? Well, so the set 1 e to the negative 9x is a fundamental solution set to the ODE for the ODE, y double prime plus 9y prime equals 0, right? Based on our theorem that we had, right? We'll do some more justifying later. We now can then claim that y equals c1 times y1 plus c2 times y2 is the general solution to our ODE. Because it doesn't matter what set of initial conditions we could also then impose on these guys, as long as it was y at some x naught is equal to some number and y prime at x naught is equal to some other number, whatever it is, we could always solve for these C1s and C2s. We'll see that maybe a little bit later as well. Okay, what does it mean to be a fundamental solution set for an ODE? You solve the equation and you're linearly independent, yeah, okay? Let me clarify that. For a second order ODE, you solve the equation, there are two functions, each one solves the equation, and those two functions are linearly independent, okay? So that's our guy there. There's another example in your book of a sample problem, ODE, where this method of coming up with the two distinct roots, remember we're still in case 1, was used, and you should convince yourself that those two functions, e to the 2x and e to the 4x, are also linearly independent for all x, okay? You can do it both ways. It's always good to do it both ways. One by showing one is not a constant multiple of the other by thinking about it this way. Okay, let's do one more. So I'll write that down for you. Show for yourselves that e to the 2x, e to the 4x are linearly independent, okay? Let's look at one more example. E to the x, let's just use y1 and y2, or y1 equals e to the x, and y2 equals e to the x plus 2, linearly independent. What do you think? e to the 2x and e to the 4x are linearly independent. I hear you out there. I hear you. What are you saying? Yeah, hey, look at this guy. E to the x plus 2, what's the algebra? What's exponential algebra? That's the same as e to the x times e to the 2, right? That's the same as e squared times e to the x, yes? Right? I can write it in either order. E to the law of multiplication, right? So what is y2? y2 is e squared times y1. And what is e squared? A constant. Because e is a constant, right? Therefore, y2 is a constant multiple of y1. Therefore, are these guys linearly independent? No. They're linearly dependent, right? Because one is a constant multiple of the other, right? So y2 is e squared times y1, right? Or, what I was saying before, right? 1 over e squared times y2 is y1, right? So y1 is a constant multiple of y2, or y2 is a constant multiple of y1. Either way, okay? So these guys are linearly independent. Constant multiples. They are linearly independent, okay? Oh, sorry, linearly dependent, whoops. Constant multiples, they are linearly dependent, yeah? Okay, so let's go back to case 1 and justify that all solutions of the form e to the r1x and e to the r2x, where r1 and r2 aren't the same number, same real number, are linearly independent. So that for case 1, we'll have our fundamental solution set in general, and then we'll be ready to start thinking about case 2 and case 3 and what happens in those cases, plus lay more foundation of the truth of all of this in the theory, right? Okay, so let's look at that. Okay, so back to case 1 in general. Okay, what is case 1, right? We have the characteristic equation gives us 2 real roots that are distinct, right? They don't equal each other, okay? What are R1 and R2 over here? R1 is 2, R2 is 4, or vice versa, it doesn't matter, yeah, okay? Here's a little aside, by the way. Provided these two guys are linearly independent, then they would be a fundamental solution set for a differential equation. Second order constant coefficient. So here we had 1 root of 2 and 1 root of 4, right? Okay. Well, what did that mean? Where did that come from? It came from what if you had that and you wanted to know what's the differential equation? You go look up where it came from, but you don't need to do that, right? So you know that came from a factored form that looked like this, yeah? Because that's the only way you're going to get those 2 roots. But if we unfoil this, right, or we foil it, yeah, okay, and unfactor it, then we're going to get what? R squared minus 2r minus 4r is minus 6r, minus and minus is 8 plus 8 equals 0. So that would have been the characteristic equation. If that was the characteristic equation, then what differential equation generates this characteristic equation with constant coefficient second order, y double prime minus 6y prime plus 8y is equal to 0. Yeah? And so that would mean that this is a fundamental solution set for this guy, and therefore if I do a linear combination of those guys, I have a general solution. Okay? All right, we're back to here. So we have, in this case, in the general case, whenever we end up with a characteristic equation that we can factor and get two different roots, right, then we're going to have an e to the r1x as our y1 and an e to the r2x as our y2, right? Now remember, we needed these two linearly independent solutions in order to generate our general solution. So think about case 2, which is the case of a double root, where you only get out one root. It's just repeated twice. It's the same number, right? You know, like e to the 2x and e to the 2x, right? Well, that's not going to be linear. Those e to the 2x isn't linearly independent with itself. So that's, you're not going to be able to write down a fundamental solution set. You got one solution, you don't have two. Where's the other one going to come from? That's one of the things we're going to address. In case 3, we are in the case when you get complex conjugate roots, not real roots at all. Well, what do we do with that? Complex numbers, what? We're talking about real solutions, right? Okay, we want to know some function, y is a function of x, and we want it to be a real valued function, right? Okay, so how do you deal with when you get complex things out? So that's what's coming up. Okay. But here we are, the general case of case 1. What do we want to do? We want to show y1 and y2 are linearly independent, right? So at this stage, you might stop the video and try to do it for e to the 2x and e to the 4x first, and then see how we do it here, and see how close you came, and see if you can think about it in the context of specific numbers 2 and 4 instead of R1 and R2. Yeah? All right. So let's do that with our more general equation about linear independence. Okay? Yeah? So let's consider C1y1 plus C2y2, right, equals 0. That's the equation we want to think about. And we want to see if we can show if these two constants have to be 0 in order to make this equation 0 for all x real. Right? So that gives us C1 e to the r1x plus C2 e to the r2x is equal to 0, right? Again, for all, a little wobbly on the knees there again. Okay, it must be the math, it's so exciting. All right, so what can I do? Well, what did we do before? It was nice, you know, let's take a look. What if we factored an e to the r1x out of this equation? You're like, wait, what? What if I factor an e to the r1x out? So what do I have left here? Good, C1, very nice. What do I have left there? If I factor an e to the r1x out of that term, what is left in that term? Well, if I was going to redistribute it, right, I'd have to get that. So it must be e to the r2x divided by e to the r1x, right? Because if I distribute it, I'd be back up there, yeah? Good. All right, so I've got e to the r1x. What exponential math is screaming at you, right? So e to the r2x divided by e to the r1x is e to the r2x minus r1x, right? But I could rewrite that by writing it, let's factor out an x from the exponent there, and I'm going to stick it here on the outside on the right instead when I factor, and I'll just have r2 minus r1, yeah? E to the r2 minus r1 x equals 0, yeah? Okay, well, what do I love about this expression? So I have a product now instead of just a sum. What do I love about this expression? expression, good. It's always positive, right? That's what matters when I'm trying to see what might be 0. So if that's always positive, and it's multiply times that, and that's got to be 0, then what has to be true? So, what do we know? Then the only way that equation is going to hold is if C1 plus C2 e to the R2 minus R1 x is 0 as well, right? Okay? Well, another way to think about this guy, lots of different things we could do. What if I bring this C1 across? Just to save myself some time. That would say this would have to be true. And then back up where we started at the beginning. What if I divide through then by C2? Yeah. So now I've got this. What do I have over here? A constant. What do I have over here? I've got a function of x, right? And that function of x is not equal to a constant, since R2, right, minus R1 is not 0. How do we know R2 minus R1 is not 0? Oh, because R1 is not equal to R2 in the case of distinct real roots. And so I've got a function of x is equal to a constant, and that's not possible, okay? Not possible. Therefore, the only way that this guy is going to get satisfied is if C1 and C2 are both 0, okay? That's one of many ways to think about it. We could add, just to create some more space here. Sorry, hopefully you got that. Okay, just to create some more space, another way to think about it is what we had done before, right? So since we got to have this, we could be like, okay, well what about when x is 0? When x is 0, that gives us a relationship between C1 and C2. C1 plus C2 has to be 0, because if x is 0, I got 1, from e to the 0, right? Okay? And then maybe we can do it when x is some other value, like, I don't know, like 1 over R2. Doesn't matter. Make something up. So what would I get? C1 e to the R1 divided by R2, yeah? Or if R2 is 0, then divide by the other guy. They're not the same. They're distinct, so they both can't be 0, right? Plus C2 times e to the x is R1 over R2, right? That would be e to the 1, right? Is equal to 0, right? Okay, well, what does this guy tell us? This guy says C1 is minus C2, just like before. We come down here and we put minus C2 in here. So minus C2 e to the R1 over R2 plus C2 times e is 0. What can we do? Factor out of C2 minus e to the R1 over R2 plus e is 0. Yeah? Question is, can that be 0? Only if R1 over R2 is 1, right? Can R1 over R2 be 1? No, because R1 is not equal to R2, so R1 over R2 is not 1, right? And therefore, because of that, this piece is not 0, because those are just specific constants. And if that product is not 0, then what does that mean? C2 has to be 0, right? And if C2 had to be 0, and C1 is minus C2, then C1 has to be 0. And we've just shown that setting this guy equal to 0 implies that the only solution is C1 equals C2 equals 0, and therefore these two guys are linearly independent. There we go. Therefore, y1 and y2 are linearly independent. And we now can rest a little more easily about our general solution in case 1. As we said, what about case 2 and case 3? Stay tuned.